Alright everybody, welcome back. In this video we're going to talk about information related to section 5.5 of AP Calculus, using the candidates test to determine absolute or global extrema. We've stepped back and talked about the extreme value theorem a number of times over the last, several units from the time we introduced it. Just a refresher of the existence of the extreme value theorem. If we have a function that's continuous on a closed interval, then it has to have both a maximum value and a minimum value on this interval. And you see a little narrative wall there for me. If we have a function that's continuous, it's guaranteed to have an absolute maximum and an absolute minimum. So it's going to be helpful for us to have some kind of mechanism that we can use in order to most efficiently determine. It's not enough to know this interval has a maximum and a minimum. We need to be able to find that maximum or minimum as well. And the mechanism we're going to use is what's known as the candidates test. So the idea behind the candidates test, we're going to identify every single one of the possible locations where the absolute extrema could occur. So we're going to find out all the places where it could occur, and then we're going to just find the value of the function at all those places where the max or min could possibly occur. And one of those has to be the global/absolute max, and one of them has to be the global/absolute min. So here's the way that we use the candidates test. First of all, we identify the candidates for where the absolute extrema could occur. There's two places that these can occur, and you'll hear me say this over and over again: critical points and endpoints. Those are the two places where we can have candidates. Then we're going to list all the candidates in a table. I normally list them from smallest to biggest. That's just kind of the process that I've gotten into over the years. And then third, we're going to find the value of the function for each of those candidates. Whichever one ends up being the largest value is the location of the absolute max, and whichever leads to the smallest value is the location of the absolute min. Okay. One last thing here, it says using the candidates test relies on the extreme value theorem, and hence we should make sure that we note that the hypothesis of the extreme value theorem should be stated. All right, so we should only be using the candidates test if we know that this is a continuous function, because otherwise we might miss out on extreme values in a situation where a function is discontinuous. All right, so let's look at example 1. Determine the absolute extrema for the following function on the given interval: f of t equals 2t cubed plus 3t squared minus 12t plus 4 on the closed interval from -4 to 2. First of all, f of t is a polynomial, so it's continuous for all real numbers. So it's continuous from -infinity to infinity. Therefore, it is continuous on the closed interval that we're talking about, since that is a subset of the real numbers. All right, so we know it's continuous, therefore the extreme value theorem applies, and we can use the candidates test. So I'm looking for the critical points and the endpoints. We can tell the endpoints from this statement of interval. I'm looking for any critical points that are in the interval from -4 to 2. So I'm going to find the derivative. That's 6t squared plus 6t minus 12. And I'm going to find the critical points where this is 0 or undefined. Since it's a polynomial, it's never undefined, so I just go ahead and set it equal to 0. Divide both sides by 6. And go ahead and factor this. And we get that t is equal to -2 or t is equal to 1. Those are our critical points. Now we're going to build our table. In the left-hand column, we're going to put time values, and on the right-hand column, we're going to put function values. Notice this is different from like the sign chart that we were using in the last couple of lessons, insofar as we're talking about the t values and the function, whereas those sign charts looked at t values and values of the derivative. So make sure you draw a distinction between those two. And I'm going to fill in all of the candidates, the endpoints, and the critical point locations. So those are all the t-values that I need to consider. Those are the only places where this function can have an absolute max or an absolute min on the given interval. And then all I need to do is go ahead and substitute those into the original function and calculate the values. So I'll substitute -4 in here for t. Let's see, that gives me -128 plus 48, so that's -80, plus another 48, so that's -32, plus 4, so that's -28. And I put -2 in there. Let's see, that's -16 plus 12, that's -4, plus 24, that's 20, plus 4 gives me 24. Put 1 in here, that's 2 plus 3 minus 12 plus 4. That's 9 minus 12 is -3. And I put 2 in here, that gives me 16 plus 12, that's 28, minus 24, that's 4, plus 4, that's 8. And so I look at these values in my table. I find the very smallest, that's that -28 right there, and I find the very largest. That's that value right there. And so I have an absolute maximum of 24 at t equals -2. And I have an absolute minimum of -28 at t equals -4. There we go. I've found the absolute extrema for the function on the given interval using the candidates test. Let's go ahead and we'll do one more example, example 2. This is from free response question number 5 from the 2018 AP Calculus exam. Since it's number 5, that means that this was a non-calculator question. We're supposed to find the absolute minimum value of the function f on the interval from 0 to 2 pi and justify our answer. First of all, f of x is equal to e to the x cosine of x. E to the x is continuous, cosine of x is continuous, therefore their product is continuous, and so f of x is continuous on 0 to 2 pi. So extreme value theorem applies. And now let's see, we need the derivative. F prime of x is equal to e to the x times negative sine of x plus cosine of x times e to the x. So f prime of x is equal to e to the x times the quantity cosine of x minus sine of x. E to the x is never going to be 0 or undefined, so we're looking for where this piece is 0 or undefined. We're looking for values where cosine of x equals sine of x in order to make that 0, and that happens at x equals pi over 4 and x equals 5 pi over 4. Okay, so now I'm going to go ahead and make my table with all my candidates. Got x on the left, f of x on the right. My endpoints, 0, and then all of my critical points, pi over 4, 5 pi over 4, and 2 pi. Okay, and now I'm going to substitute these values one by one into the original function. And that's probably the hardest part for this particular problem, is calculating the values of f of x, especially since this is a non-calc section. I put 0 in here, that's e to the 0 times the cosine of 0. E to the 0 is 1, cosine of 0 is 1, so that product is 1. Pi over 4. E to the pi over 4 is just e to the pi over 4, and the cosine of pi over 4 is square root of 2 over 2. So this is root 2 over 2, e to the pi over 4. Then I put 5 pi over 4 in. e to the 5 pi over 4, and cosine of 5 pi over 4 is negative root 2 over 2. And then I put 2 pi in here. E to the 2 pi is e to the 2 pi. Cosine of 2 pi is 1. So this is just equal to e to the 2 pi. So I look at all these values and I'm looking to figure out, hey, which one of these is the very smallest, because the problem asks us to find the absolute minimum. I look at these values and, I mean, looking at the raw values, it's hard for me to tell their relative sizes, but I do know that this one is negative and all the rest of them are positive, and therefore that's going to be our minimum value. And so the absolute minimum is negative square root of 2 over 2 e to the 5 pi over 4. Since it is the only... And I don't necessarily even need to state this last part, but since it's the only negative value at a critical point or endpoint, when we're using the candidates test, this table is your justification. So having a table with the endpoints, the critical points, and all of their y values presented, that is your justification, and you can, ride on that, and that is everything you need to say that that's the absolute minimum. Okay, go ahead and do some practice on these problems, and we'll come back next time with section 5.6, which is, oh my goodness, what's section 5.6? What comes next? Concavity? I think so. Yeah, determining concavity of functions over their domains. So that's where we're going next time, to section 5.6. All right, everybody, have a good rest of your day, and see you next time.